right, so in real life applications, we often use something called parametric equations. So parametric equations allow us to write x equations and y equations in terms of another variable, usually t for time. Okay, so if I'm like launching something into the air, I think I'm an example of a human cannonball, and I'm launching it into the air. There's going to be a certain time that it takes to travel horizontally, and there's a certain time like vertically. And the vertical axis has to do with like gravity, right? Gravity's pulling it downwards, but in the horizontal one, gravity's not affecting something horizontally, okay? It would continue to go out horizontally forever if there wasn't gravity that actually pulled it to the ground. Okay, so we'll talk a lot about that eventually. All right, so it says consider the set of all ordered pairs. Okay. Okay. So using these, this little t-table. All right, so we're going to plug in time. Well, it's not really t equals time equals -3. We can't go back in time, right? But we're going to plug in t equals -3, -2, -1, 0, 1, 2, and 3 in this t-table. Do you guys see how this t-table is different than what we normally do? Because there's an x equation and there's a y equation. That's what parametric equations look like, okay? So we're going to plug in t equals -3 in for the x equation, and we get -3 plus 1, which is -2. So just fill everything in. I give up. It's not working. All right, and then plug in t equals -2, and you get -1. All right, then we plug in 0, we get 1, 1, 2, 3, and 4. All right, easy to fill in, right? All right, then we start plugging in -3, -2, -1, 0, and so on into this other equation. So we get 9 plus 9 is 18. 4 plus 6 is 10. Did I mess something up? 36? So it was 9 minus 3 times -3, this one. So I think it's 9 plus 9, right?
But it's 9 squared.
It'd be the 3 squared, yeah. Okay. All right, so then we have -1 squared is 1 minus 3 times -1, so plus 3, so 4. And then 0. 1 minus 3 is -2. 4 minus 6 is not 4 minus 6, so -2. And then 9 minus 9 is 0. All right, so we get that. You don't like that? Too much to fill in, huh? So what happens is we have all these points that we could plot. So I could plot -2, 18. I could plot -1, 10. I could plot 0, 4, 1, 0, 2, -2, 3, -2, and 4, 0. What shape do you think it's going to end up being? Yeah, it kind of looks like it's going to be a parabola, right? So you can start kind of plotting those things. So we can go back and forth between parametric equations and what we call rectangular equations, like our normal xy equations, like that we can plot on the Cartesian coordinate plane, right? We can eliminate the parameter by combining those equations. So if I have the two equations, x is equal to t plus 1, and I have y is equal to t squared minus 3t, I could solve one of those equations. See how this one's pretty easy to get the t by itself? If I was isolating the t, I would have x minus 1. Did you guys get that? What do you think I'm going to do to eliminate that parameter, eliminate the t in this problem? I'm going to put this into this, right? Does that make sense? So if I replace my t's with x minus 1, I get x minus 1 squared, right? Minus 3 times x minus 1. I'm replacing those with my x minus 1. And then I could FOIL it out. Oops, not y squared, sorry. Y equals x squared minus 2x plus 1 minus 3x plus 3. So we'd get the equation x squared minus 5x plus 4. Okay, and that's what that parabola is. It's x squared minus 5x plus 4. Right? If you factored that and found the x-intercepts, you would have x-intercepts at 4 and 1, right? And you could find its max and min, right? Negative b over 2a, you could do all that. That's that exact same parabola. Okay, is that kind of weird? Are you guys like, why do we do this? I think people always think at this point, they're like, why do we do this? Because this just makes it more complicated. It was just that parabola, right? But it makes it better when we talk about projectile motion, when we're throwing things into the air, right? So if I'm throwing a football, or if I'm kicking a soccer ball, or if I'm launching a missile. Let's try practicing eliminating the parameter. And then next section, we're going to talk about projectile motion. All right, so which one looks easiest to get the t by itself?
X.
Yeah, let's get the x equation. So I'm going to divide by 2, and I get t. And then I plug it into the second equation. So I'm going to plug in x over 2 and replace it when replacing that t. So it's really going to be, let me write it in a more familiar form. Do you guys see how it's 3 over 2x minus 1? So it would be a line. And it says graph in parametric mode to check. So we're going to use our calculators in what we call parametric mode. Okay, so go into your calculator. All right, and we're going to have y equals, or I'm going to go to mode, sorry. And go down, do you guys see where it says function, and then next to it, it says PAR? So we're going to graph in parametric mode. Okay, and when we go to our y equals now, look what happens. See how it's different? So we have x and y. So it's saying in our first equation, we have an x1 and a y1. So my x is going to be 2t. And look how if you hit the x button that we normally hit, what happens now? It becomes a t, yeah. And so then I have 3t minus 1. And I hit graph. And so what happens is it looks like a line, but it doesn't look like the whole line. Okay, that's like if we were doing the t-table that we had before, like on that last example. This is saying if I started out with t equals 0 and continued. But could t be anything? Sure. Like we could have negative values for t. So if you go to your window, you can make t max, or yeah, t max and t min. Where is it? T max. Yeah, t min. I can make that t min. I can make it smaller. I could go from like -10 to 10. And then when I hit graph, I do see the entire line. Does that make sense? Okay, so we have both of those. All right, so let's do this next one. So we did get the line that had a y-intercept of -1 and a slope of 1, 2, 3 over 2. So we got that line. All right, so let's do the next one. So let's solve for x or t or whatever. So see how t is equal to x squared? So if we plug it into this equation, we get y equals 2 times x squared minus 5. So it's a parabola that has a y-intercept of -5. And is it an upwards or downwards parabola? An upwards one. So if I clear those out and check, if I have the square root of t, and I have 2t minus 5, and I hit graph, see how I get that parabola? Okay, but I'm only getting part of it. Okay, tell me why I can't plug in negatives for this example. Yeah, what do you think, Greta? So it looked like part of that parabola. So 1, 2, 3, 4, 5. But we didn't have anything over here. And you can check, like you could go to your window and you're like, ooh, did I have t values that were negative? And we do. We have t values that are negative. It goes -10 to 10. But imagine I was setting up with a t-table, and I had my t, and I had my x, and I had my y. What if I try to plug in like -4 for t? Yeah, x is equal to the square root of t, right? So if I plug in -4, I'm going to have the square root of -4. And we can't do that. We don't have eyes on this graph, right? So it's not going to work. So all of those negatives won't work. So no negative values for t because x was equal to the square root of t, right? Does that make sense? You can't put negatives into that. Okay. All right, so the next one. So it says sketch the curve given by x equals t squared plus 4 and y equals t over 2, where t is between -2 and 2. Okay, so for between -2 and 2, I gave you the points because I didn't want to go through and do every single one of those points. So we have the points there. So if you plug in -2, you get 8 for x, and you get -1 for y. So we're going to have 8 comma negative 1. I'm going to put this in the bigger mode. So go over 8 down 1. And then we have 5 negative 1/2. So somewhere, whoops, I missed the 5, didn't I? 5 comma negative 1/2. And then I have 0, 0. And then I have 5 1/2. And I have 8 comma 1. So can you tell what shape this is? It's a sideways parabola, and it's a super, super skinny one, right? So it's a super skinny sideways parabola. So that's like that. All right, and if we're only between negative 2 and 2, it actually doesn't continue past those points. It just stops. It kind of has like endpoints there. Okay? So let's try that. So if I'm graphing it on the calculator, and I go to my y equals button, oh man, whenever I pause my thing, it does not like that. All right, so if I go to my parametric equation, you guys already have it set like that, but so if I hit y equals, and I put in this function, t squared plus 4 over t over 2. All right, and then I have to hit window first. I have to adjust my t-min and my t-max. So what's my t-min and what's my t-max? Negative 2 to 2. And so when I hit graph, it's going to graph that little parabola. Why is mine shifted over? Did I forget it? Did I do it wrong? When I graphed it, did I do it wrong? Maybe this, oh, the zero's wrong, right? This should be what? That should be 4. So I did my picture wrong. So it's not as skinny as I think it was. It's a good thing we used our calculator to verify that, huh? So it's actually going to be right there. All right, so it's just a little tiny parabola on its side. All right, so eliminate the parameter to write the rectangular equation. So if I try to solve one of these for t, which one looks the easiest to solve for t? The y, right? So I'm going to write y times 2 is equal to t. And then I replace, so I get x equals 2y squared plus 4, like that. So I have x equals 4y squared plus 4. Okay, I don't know if you guys remember from Algebra 2 when you guys did conic sections. Have you guys seen people in Algebra 2 doing that right now? We always had like x minus h squared equals 4p times y minus k. Or we had x minus h had the 4p. And then y minus k had the squared. So one of those. I always say there's a little bit of flair on both sides. One of them has the 4p, one of them has the squared. Would this be a y squared equation or an x squared equation? It's a y squared equation, so it's a parabola on its side. So it's like the bottom one. So really what we would do is we would pull out that 4 to get in like the standard form. So we'd have 4 times y squared plus 1, and then we would divide that 4 over. Well, actually, kind of, maybe not. Maybe I'd add let's add the 4 over and then divide by 4. Or subtract the 4 over. So it'd be minus 4 divided by 4 equals the y squared part. So it would look like 1/4 x minus 4 equals y squared if I was trying to get in that standard form. So don't worry too much about the standard form right now, but we are going to do a review of conic sections soon. So we'll be doing that again. I know, so exciting. All right. So we used our calculator, we checked our window, and we're good. All right, so next thing. So it says we can graph parametric equations by hand, and we can use our calculators too. So if you have a certain domain for your t values, we hit window, we adjust the t-min and t-max like I've been doing, right? So here's an example of what you would see for 3 different domains. So if we had x equals t squared minus 3 and y equals 3t, if I gave you a parameter from my t value from -3 to 1, it would only graph this portion of it. But if I said -2 to 3, it would be this portion. So if I said -3 all the way to 3, it would graph all of it. Does that make sense why we're doing that? Because we would have the t table and we plug in those different t's and we wouldn't get all of the points, right? We're kind of stopping part of the curve. You know what I'm saying? Okay. So let's graph sine of t and sine of 2t from 0 to 2 pi using our graphing calculator. So we're going to go into our graphing calculator and we're going to put in sine of t. And we're going to put in sine of 2t. And under my mode, notice how it's in radians. That's what we want because we want it to go from 0 to 2 pi. So under window, since we were given a restriction for our t values, we want those t values to go from 0 to 2 pi. So we can actually put the pi button in. So 2 pi like that. And when you hit up or down, see how it changes it to 6.283, blah, blah, blah. All right, so when we hit graph, we get something really tiny right there. It's like a little infinity sign. Looks like that. Okay, that's what we got. There's a name for that. It's called a lemniscate. All right. So what about the next one? So it says sketch the curve represented with parametric equations, then eliminate the parameter, find an equation with only x and y to write the rectangular equation. All right. So we have, I don't know if I want you to do this by hand or not. If I didn't give a t table, we'll just do it on the calculator. So we have 2 times t plus 1. And then we also have, whoops, I did an extra parenthesis there. We have 3 minus t. All right, so we're going to hit graph. And it only gives part of it. Well, that's because our window is still in that 0 to 2 pi. So I could do like negative 10 to 10, something like that. And we'll see if we have a whole curve. Okay, so it looks like a line. It looks like a line that has a y-intercept of 1, 2, 3, 4 maybe. And you could count the slope as well. Okay, so let's see if we can get that line. It looks something like that. So if I solve one of these for t, so let's say I add the t over, and then I subtract the y over. And I plug into the second equation. I get x equals 2 times the t was 3 minus y, and then we still had a plus 1. So we get x equals 6 minus 2y plus 2, which is 8, and I'm going to subtract the 8 over, so I'm going to have x minus 8 equals negative 2y, and then divide by negative 2. So I get y equals negative 1/2 x plus 4. Does that have a y-intercept of 4? Yeah, and it has a slope of down 1, right, 2. So I'm guessing if I'd counted, this would cross at 8, right? Okay, that's the line that we have. So we know we're good. Pretty easy? All right, you guys try the next two. See, it's pretty hard, so try the next two. Okay. All right, let's see. So you solved for, I'm guessing with the y equation, it's easiest to solve. So we get t equals y over 5. And then you plugged in. So you had y over 5 squared plus 1, which I saw. Oh, yes, minus 1. Kenzie got me. Bonus point for Kenzie. So we get that. So it is a parabola that's on its side, right? Because it's an x equals y squared equation. All right, if you wanted to see how to put that in, like into your calculator with our normal y equals function notation, like our normal setup on our calculators, you would have to add the 1 over, multiply by 25, take the square root, right? And do plus or minus. Okay, so we could do that. So let me kind of write that in parentheses. It'd be like x plus 1 multiplied by 25 equals y squared, right? So 25x plus 25, and then it'd be under a square root, and we take that plus or minus. So we'd have to, let me just get rid of the parentheses. It's in another color so you understand what I'm saying. So if I was going into my regular, function notation mode, and I tried to graph that, just like we did, before we learned this parametric equation, we'd have to put in two square root functions. So we'd have a positive square root function, and that would give us like the top part of a parabola. But I'd also have to do the negative square root of function. So it'd be negative square root of 25x plus 25. And that would give me the bottom part of the parabola. Okay. And then there's always like a little space there, like your calculator kind of shows you that the top and the bottom part of that. But it would cross. What would equal 0? Yeah, what would make it equal to 0? If you had negative 1 over 25 or something. All right, so we're getting a full parabola. So if we go back to our mode and we put it in parametric mode, and you graph it. Did you guys try that? So you have t squared minus 1, and you have 5t. When you graph this, see how it gives you the same thing, and it's actually going to go through that. So you can see the two parts are actually combined, right? So our calculator does that so we can see a top function and a bottom function. Have you guys ever graphed like a circle on a calculator and it doesn't show where it meets? It's kind of annoying that it doesn't do that, but they do meet. All right, so this one, kind of complicated. I'm guessing that you guys probably thought to do like the y equals equation and solve for t, which would involve a plus or minus when you take the square root. The easiest thing to do is actually take this one. How do we get rid of the natural log? Yeah, so we're going to do, remember how this is like, that's like log base e of 2t, right? That's what natural log means. So it's e to the x, right? So if I want to get rid of a natural log, I just do e raised to both sides. So if I had e raised to the natural log of 2t, it ends up becoming just 2t, right? So I'm going to get 2t, and then I divide by 2, so I get e to the x over 2. So when I plug in, I get y equals 2, and I have e to the x over 2 squared. What do you guys think e to the x squared is? What's a simpler way of writing that? E to the 2x. Yeah, e to the 2x. Remember we multiply our exponents? So we can say e to the 2x, and then we had over 4, and we still had multiplied by that 2. So do you guys see what's going to happen? The 2 and the 4 will reduce out and become a 2 on the bottom. So that would be the most simplified form of that, which you could look at on your normal function notation. I know it's annoying going back and forth between our two modes, but if we graphed it with our function notation, and I went to my y equals, and I graphed e to the whatever. So if I do e to the 2x divided by 2, when I hit graph, I get this, like an exponential function, right? Okay, so if I go to my parametric mode, I end up getting the same thing if I put this in. Yeah, Greta? So you use function mode when you don't have a t, so like when you have it in that form. So if you want to check that the two are the same, you would go back from that function mode back and forth between the parametric mode. Yeah, and like I was saying, parametric mode is basically like, I think they invented it for the questions that we're going to do with the projectile motion where it matters for time in the x direction and the y direction. Okay, so that's kind of why we have that. And the last thing, well, it also is for polar coordinates, which we'll show you. So the last thing talks about, if you had cosine of t and sine of t, so x is equal to cosine t and y is equal to sine of t. I went ahead and filled in the chart, but you could do this by hand, right? That 0.707 is root 2 over 2, right? You could find all those things. And if you graph these, so if you did cosine t, anybody have a guess of what we're going to get? Whoops, I need to go into a circle, you think? Did you already try it? You're right, it's totally a circle. Why did you guess a circle? Yeah, it's just like the unit circle, right? Does it make sense? So we get that tiny little circle there, which is the unit circle. Amazing. So we're going from 0 all the way around. So if you did every single point at one at a time, it would start sketching around like that. Does that make sense? Going all the way to 2 pi, it would find all those things. Remember how every single value is cosine of theta. So we'll say cosine t sine t on the unit circle, as Greta was saying. That's what's happening. It's plotting all the points that are on that unit circle. So for part B, it says, well, what happens if we adjust it and we have a bigger, see how it's 2 cosine t and 2 sine of t, what would happen? It goes around. What's the radius now? Is it still the unit circle? Does it still go out to a 1 and a negative 1? Yeah, it's going to go out to 2 and negative 2, right? Because all those values that we had before are now going to be doubled. Yeah. Greta?
So when it's like between 0 and pi, what does that mean?
I don't know. What do you guys think that means?
I know it's like in the first quadrant.
Well, not just the first quadrant, the first and the second quadrant. So we're going to have here here to here, and it's just going to be a semicircle. Makes sense? We don't go all the way to 2 pi, so it's just the top part of the circle. So then what's this one going to be? All the way around. What's its radius? Does it go all the way around though?
No, it's just the bottom.
It's the bottom part. Exactly. Does it make sense? So we can get those. And then the last thing I want to mention is this is leading into, I mentioned polar equations. So if you go into mode, and you guys see how it says function, parametric, polar. If you did polar equations here, and you went here, you have r equals. If you put something in like 4 sine of 3 theta, and you hit graph, you're going to get cool things like that. Or if I made it, ooh, let's try something else. What if I did 4 theta and I made it bigger here? Look at that. Isn't that crazy? You're getting flowers. Or if I do theta, look what's going to happen. Well, let me make it a bigger. It ends up being like a spiral. So there's things that we're going to be learning, like how to graph these things eventually, that I think are really cool, and you'll really like the polar equations. So this is what parametric equations is kind of leading to, the projectile motion and also polar equations. Okay, so I know it seems weird right now, but there is a purpose. I promise we'll get there.